welcome to this screencast about the overview for ICS 211. Trying to build the mental landscape, give you a picture or an idea of what programming is and what computer programming is. Just a very brief overview. Don't worry if you don't understand the material, or this is not going to go into depth. We'll cover this much more deeply as we go along in the semester. So what is the fundamentals of a computer? Basically, it's a machine, it's a device, it's a thing that has three basic pieces to it. The first piece is input. We can put information or things into this device that can be range from text, location, sound, all these different kinds of things. Images. It then does some processing on this input, so you have some data or some things, and you do some processing, you do some manipulation, you do some math, you do all sorts of kinds of processing on the data. And then if that's where we stopped, be a very boring device, you have no way of knowing the answer to the problem. So it has a way of outputting data, hopefully the answer or whatever, to the outside world. So we can provide input to the device does some things, and then it produces output that we can then potentially put back into it and then go on and on. But if you need to be able to put things into the device, it needs to do some stuff to the input, and then it produces output. So that's very simple. That's what a computer is. It's got those three parts. Input, it does some processing, it does output. So what is the processing part? We're going to talk about most of the computers today are von Neumann architecture computers. So they have some input that comes in that we talked about. The processor has a central processing unit that consists of a control piece, a thing that does controlling, and then it has arithmetic logic unit, so it can do some math. Very simple math, normally multiply, divide, add, subtract, and that's probably about generally it. You might be able to do some other kinds of math. And then we have this idea of the memory unit that allows us to remember things. So we have the place where we can store our data and our, as we'll see next, instructions. And then we have an output device. So again, so if we don't have a way of getting anything from the outside, we can do all the processing we want, and if we don't have a way of outputting, it's not worth anything. So we have to get data from the outside, do this processing, and then produce the output. But the processor breaks down into those two basic pieces: a control unit, central processing unit, and a memory unit. So how do modern processors work? We store both the data and the instructions or the program in memory. So we're storing them in memory. They're both in memory. Now we have the control unit, which keeps track of where the program is. So it has a program counter, so it knows where we need to do the next instruction. And it has some other things like the register to have the instruction. And then the arithmetic logic unit may have several registers to keep track of different things where you can do, maybe I need to add two numbers together or something. So how does this all work? So basically, the computer has a very simple fetch and execute cycle. And it just keeps doing this over and over again. It's just going to keep doing this cycle of fetching and executing, and it doesn't stop. It just keeps doing this. So the first step is to fetch. So the program counter has the position in memory of where the next instruction is. So in this case, it's at position, that's binary number, so that's 6. So we go to location 6, grab that instruction, put that into the control unit, and then we need to potentially decode the instruction, because sometimes it's encoded, so we need to manipulate it. And that instruction tells the CPU what it needs to do to execute it. It turns things on, it turns things off. That is the instruction that the CPU then executes. So that instruction might say, in this case, output the value at a particular register into a certain memory location, or potentially it might say, go fetch some data from a memory location and put it into the arithmetic logic. Or maybe it says, just add those two registers together, or divide them, or shift them, or whatever. It's you execute whatever that instruction is, one step. And then you increment the program counter. So we say there's the next location that we're going to fetch the next instruction. So we did increment it, so we're going to go grab location 7. We're going to move that instruction into the register. We're going to potentially decode it, and then we're going to have the CPU do one thing. It's going to execute that instruction, possibly producing, updating the memory, possibly not, just maybe updating a register, whatever. We just keep doing this cycle over and over and over again. We grab the instruction that's pointed to or at the location that the program counter counts. Some instructions might change the program counter by more than one. For example, if you wanted to go do something else, you might change the program counter dramatically, but you basically just keep doing this cycle of fetch the next instruction, execute the next instruction, fetch the next instruction, execute it. And that's all the CPU does, fetch and execute. So how do we deal with other kinds of things? Like how does the CPU know when there's data available for, like, someone pressed a key or moved a mouse or you got an email or the bad guy shot you in your first person shooter or whatever? Well, there's a couple of ways. Basically, the simplest way is that the CPU, because again it's just doing this fetch execute, goes and says, hey, keyboard, did you press a key? Nope. Okay, I'll go on to the disk drive. Did you have any data for me? No. Network, do you have any data for me? Memory, are you ready to give me data? No. Display, are you ready to give me any data? No. Okay, so I'll go on and start asking the question again and again. So I just keep asking each device if it has data for me. The CPU does. That's pretty bad way of doing it because disk drives are much slower as compared to memory in the CPU, which works very fast. And how often do you get an email? Well, maybe you get one every 10 minutes or 5 minutes or 1 minute, but that's still a huge amount of time between receiving the email than what the CPU is doing. The CPU is doing very fast fetch execute cycle. So it's a very inefficient way of getting data from the outside world, getting your input. So what's the other way to do it? Is we use interrupts. So what we do is when the device is ready, it says, I've got data for you, CPU, it signals a interrupt to the CPU or to the I/O controller. So then the CPU, who's in there executing the fetch execute, doing the program, doing something, needs to go, hey, I got to handle this input from the device. So I need to store what I'm doing now. So it's got to store the program counter and all the registers so it remembers where it was and all the stuff it was doing, so it stores it. It can then now run a little program to handle the interrupt. For example, if it's a disk saying I've got data for you, we could then run a little program to move the data from the disk drive into memory, or vice versa, back out. But the CPU is running the fetch execute cycle for this handler. So it's just doing whatever, it's dealing with the data from the device. For a key press, maybe it's just moving that whatever key was pressed into memory or perhaps into the registers. And then once it's done handling that interrupt, those are normally fairly short little programs, it then resumes work by restoring whatever it was doing before the interrupt arrived. So it needs to restore the program counter, restore all the registers so it now knows where it is, and it can continue doing the fetch execute cycle on this old job that got interrupted for a little bit while we had to handle this data that showed up. So what this does is it allows the CPU to be working very quickly on these tasks, and when you get a key press or something, you just, for a very short period of time, you go out, handle it, come back, and it's very difficult for humans to see that actually happens. So you don't really notice that, oh, my program or my game or whatever stopped working when I was pressing the keys or whatever. So it's because they're fairly quick to handle, and the CPU is really just doing this fetch execute cycle over and over again, and either doing the program or being interrupted to handle other outside events. So the CPU is all this binary instructions and binary data. So the CPU or computers really only understand machine language. Now you have to have a different machine language for every different type of architecture in your computer. So let's say you had a 16-bit or 32-bit computer versus a 64-bit computer. That's a different machine language because you have different instruction sets. It's all binary. It's very simple binary instructions to say, go do this, go do that. But it's very difficult for humans to write programs in binary ones and zeros. It's just very difficult. It's practically impossible. I marvel at the people that write machine language. I don't know how they do it. So what we did, as people did, is they said, this is very difficult, and the computers need this machine language, but we don't, as people, don't like thinking in ones and zeros. We like thinking in higher level languages. So they came up with many, many, many higher level languages like Java, Fortran, C++, COBOL, Lisp, Haskell, Prolog, Python, JavaScript, all these different high level languages that allow us to use letters and numbers and other things, control structures, etc. But now we have a problem. The computer doesn't understand how to run a Java program. It only understands machine language. So we need to convert our high-level language into this machine language. And we need to convert this high-level language into the machine language that the machine understands. So if you convert a high-level language like a Java program to a Unix workstation, that's different than doing it on a PC or doing it on a Atari 2600. So there's two ways to do this. We've come up with two ways to do this. One is you have a compiler. It takes the code, the high-level language, and converts it into machine language. So you have a file that has all these ones and zeros, and so the program counters start at the beginning of the file and start executing, and each of those data, those instructions, are written in actually the machine language that the computer that it's running on understands. It has sections for storing the data for like all the variables you wrote in your program, etc. And then you have the instructions. And so the compiler actually takes your high-level language and converts it into the machine language. The other way to do it is you write this program that interpolates each high-level instruction one by one and converts them into the machine language instructions and then executes them. So you take the first bit of code or the first line of code, and then in the high-level language, convert that into how many different low-level machine language instructions you need, and then you go and do that. And then you take the next instruction and you convert it and run it. So the interpreter is actually not converting the entire program into machine language, it's doing it one instruction at a time. And this allows for flexibility because you can actually change things as it's running. Whereas in the compiler, you have the output machine language in a file. So how does Java do this? Well, Java decided to combine both compilation and interpolation for flexibility. So you can have these Java programs that are compiled using the Java-C command into Java bytecode, which is another lower level. It's still a high-level programming language, but it's bytes, so it's ones and zeros, that then gets interpreted by Java virtual machines. Now, Java virtual machine, you have a different Java virtual machine for each different operating system that you want to run in. So, for example, you have a Java virtual machine for Mac OSs, Java virtual machine for iOS, you have a Java virtual machine for Windows and Linux, and you have Java virtual machine for the different versions of Windows and Linux and Mac. So what this does is you can now take this one Java program, high-level language, you compile it into the bytecode, and you can run that bytecode on a whole variety of different machines, like a Mac OS, Windows OS. And so what that does is it does provide security, because now we can validate the bytecode, which is simpler than trying to validate the Java program. The virtual machines can enforce some rules, and they all enforce the rules the same way, so it's much easier because the interpreter is a much simpler program to write than the compiler, because the compiler has to deal with the entire language, whereas the interpreter is just dealing with the bytecode program. So it's a very flexible way, and it provides additional security. And now we can just send the bytecode over the internet, so we can send our Java code over the network, and it's secure. So what's the next thing? What are the basic building blocks of programs? So I've sort of implied there are two basic things, or aspects of programming. We have the instructions that we're going to execute, and we have the data that we're going to use the instructions on. So what's the data? And again, all of these are stored in memory, in the same memory, not at the same place in the memory, but they're all stored in memory. So data, well, there's variables, right? We have this idea that there's variables, they hold data. They're a way of naming a location, or they name some point to the memory location, because everything's in memory, but you really should think of them simply as they're boxes that can hold things. So, they can hold different kinds of things, they can hold many things, but they hold a thing. So we can have this idea that we can name something and we store it. We also have the idea of types. So there's different kinds of things. So like we have an integer versus a floating point number versus a character versus a string versus an instance of a human being. There's all kinds of things. They do have the idea of a type. And in Java, it's a strongly typed language, so you can't do assignments and things between things of different types. It doesn't make any sense to be able to say, oh, how many, or you can't add apples and oranges. That doesn't make any sense. So they're different types. And the third concept between data is the idea of assignment. We can say, we're going to take something and store it in our box. This is how we get the stuff in the box. We do it by assignment. So the interest box is going to get the value that the principal box points to right now times 0.07. So that's how we fill the interest box. Now, do we know what's in the principal box? Well, we can look it up, but since it's a box, it could change. So the idea is that the answer to this equation, this statement, we don't know until we know what the value of principal is at the time that this assignment was made. So variables are names that point to locations, but they're really just boxes that hold things, and those boxes have a specific type. Java has a specific, they have a specific type. And then how do we fill the box? We use the assignment. So what's the other half? Are the instructions. So the first idea, as we were talking about with the fetch execute cycle, computers just execute a sequence of instructions. They do one, and then the next one, and then the next one, and they just go straight down the page, if that's the way you want to think about it, but they're going to go do the first one, and then do the second one, do the third one. So it's just a sequence of instructions. I'm just going to do the first one, second one, third one. Now, to write a program that does something complicated or even interesting, it's kind of difficult if you just have to say, go straight from A to Z. I mean, there's no going left or right or making a decision or anything. So it's just do the first one, do the second one, do the third one. So they have to add a new idea of just beyond the sequence of instructions. We want to add control structures which can change the flow of the control. So instead of going just 1, 2, 3, 4, 5, 6, we go 1, 2, and then if there's something's true or false, maybe we do 7, 8, and then we go back to 3. So it's a way of changing the flow through those instructions that we put into the high-level language and eventually into the machine language. Because again, we're getting eventually to the machine language instructions. So what are the kinds of control structures we have? There's basically two kinds. We have loops. We want to do the same thing again and again and again, or similar things. So again, we're doing a sequence of instructions, but we want to do it again. Sort of like, if you're wrapping presents for Christmas, or you're making 100 sandwiches for your friends, you would probably create sort of a production line and say, I'm going to make one sandwich, and then I'm going to go do that same process again and again and again until I have enough done. So it's just, we're doing a sequence of instructions or something again and again. We're going to loop over the thing again and again. Now you could do this in a straight line if you just keep repeating yourself again and again and again and say, oh, do this, do A, do B, do A, do B, do A, do B. But it's much nicer to have a loop that allows us to say A and B in there, and then we have some sense of, we know how many times we want to do it or what the conditions are to how many times we do the loop. And then we have another concept of branches. So that's like, oh, do I want to go left or right when I come to a fork in the road? We make a decision and we can do alternatives. Now there's more than just left or right, true or false. There's a whole bunch of different kinds of branch statements. Certainly in Java and many other languages, we can make a whole bunch of very different decisions. But basically the idea is we compare or we check something, and then we're going to do a bunch of statements based upon the value or the result of that comparison. So in this case, if the principal is greater than 10,000, then we actually, the interest rate or the interest earned is larger, so the rich people keep getting richer, or if you don't have the $10,000, well, sorry, you get less money. That's sort of the idea of branching. We're going to make a decision based upon an evaluation of something, and we can do one thing or another, or potentially many different things. And then another way, so we have the control structures, basically just looping and branching. And then there's the idea of bigger programs. We don't want to have to do all that stuff again and again. We don't want to have to write all that again. We want to break it up into chunks that we can reuse again and again. So those are subroutines. They're basically just a bunch of instructions that are broken or collected together. They're named, sort of like variables are named, and then you can then call them and have the computer execute those instructions. So here in this example, we say draw a house. So we could say, oh, I want to draw a house. Later on, I can say draw another house, draw a house. So I can break up my program into named chunks that I can reuse again and again. And I can pass in parameters, I can get different return values, etc. We'll talk about that later on. But the idea is that we want to break up our program into smaller and smaller chunks so that we can reuse those chunks. And that goes back to, starts with the idea of how do we build these programs? We must actually design them because we're trying to solve a problem. So they started off, one of the key features of programming is to use a process called structured programming, where you solve a large problem by looking at the problem and breaking it up into smaller chunks. So, and then you take that each smaller chunk and break it up into smaller and smaller chunks until you can solve the smallest chunk. Just keep breaking it down until you solve the problem directly. So it's like eventually you're going to say, oh, I can just say A equals B, I solved that problem, and then I combine that piece with another piece, and then eventually I combine all my chunks together, and I have solved the large problem. Now, that's called top-down programming. Now, one of the issues with top-down programming is that each different big problem may lead to different solutions, so you don't have a lot of reuse. So like if you're trying to build a game for sixth graders and you do your top-down programming, you come up with all your solutions, you build it back up, but then you want to do a game for college students, you do it again, you may find out that your breakdown of the problem did not end up with reusable pieces, so you had to resolve the problem every time. So instead of doing that, another idea is you start at the bottom and you look at solutions combine them to solve bigger solutions. So it's like the bottom up versus top down. So you start with the little bottoms and you make them reusable. So it's like, oh, I'm going to have, for example, maybe a subroutine or a module that calculates your score in a game. I can then use that module in a whole bunch of different games as long as they had the concept of a score. So this is a way of starting sort of at the bottom and building, using these blocks or modules to solve bigger problems, whereas top down, we start at the big problem and break it into things, and eventually, hopefully, the top down and the bottom up mesh, and we can say, oh, here's my set of bottom up blocks that solves my top down, and they're reusable. So we want to build these modules. These modules have a well-defined interface, so we know exactly what they have, what they do, and how they do. We don't care about how they do it. They just do it, and we know what we need to provide them to do it. So it's like a magic machine that does the work. And the idea that we don't care how it does it is very important, because it's called information hiding, but it's like it allows me to reuse that box again and again without having to actually know how that sucker works. I just get to use it and get it, and so I can combine these things again, I can reuse it again and again, and I don't care if they're using some screwy math in there. I just know that it's going to give me the right answers, or does what I needed to do. So we expand on that idea to now talk about object-oriented programming, which we're talking about this semester because we're using Java. And so the idea is that an object is a module that has both this data state, it has an internal state, so it knows some things, it's got some data, and it has a bunch of messages or subroutines, they're also called methods when we talk about object-oriented programming, that is what it can do. So you can say, oh, I want to create this object, like an example would be, oh, I want to create a student object that represents myself. It's got a name, and it's got a GPA, and it's got a graduation, hopefully graduation day, and it has a bunch of messages like, oh, what is your GPA? Or update your GPA to something because you got a new grade, or those kinds of things. So we've encapsulated these modules into the concept of an object. So it's a thing that has state, and it has a bunch of subroutines or methods or functions that it understands and works on the data inside itself. So now, what if we said, oh, now we have these objects, these modules that work together. Well, what if we have things that are similar? So it's like, oh, we have more than one student. So we have this idea of there are these classes that are a bunch of objects that share the same type of data and respond to the same messages. So it's like all students know how to return their GPA. We'll answer that question. All students can update their GPA. All students have a name, and they'll answer your name, or you can set their name. So these are ideas of the class is sort of a description of the things that are common between the individual objects. Individual objects may have different data, but they respond to the same messages, but they may have a different answer to the same message. My GPA different than your GPA. And then inheritance is where we say, oh, we can take these classes and say there's sort of this idea of a person, and then a student is not a sub-person, but is a subclass, or inherits from a person because a person has a name and all this information, but a student has some additional information or state and may have some additional methods to, and there's inheritance which defines these relationships between these classes. It gets very big, and there are huge class inheritance hierarchies. Java's got a monstrous one, but don't worry about it. The idea is each individual object is a thing with some data, and it understands some messages. The class describes all the messages and the kind of data that each individual object has, and then there's relationships between classes. So, not to overwhelm, we're going to do a very brief, because this class we're going to do some talking about GUIs and interfaces. Back in the day, we used to use the command line interface. Very simple, typing on a text, ASCII text, saying to do things. Great thing to learn. I highly recommend you learn how to use your command line interface for whatever machine you're using, because it can be very helpful to be able to get down at the command line interface and be able to manage your computer. It's very helpful. There are a lot of tools to help you do things. But now, we're basically in a GUI, graphical user interface. It's very nice to have a mouse that moves around the screen. You can click things, you can drag and drop and all this stuff. So we're going to learn very brief introduction about how to make graphical user interfaces. We'll also start off with command line interfaces because that's very simple, and that's the easiest way to start. So that's sort of the state now. And then the last sort of state of where we are is the internet. Back in the day, in part of the history, most computers were standalone. Now they're often connected together on networks. The largest network is the internet. The internet sends data to the computers via packets using the internet protocol. Each computer has its own IP address. It has another protocol, transmission TCP protocol, that allows you to guarantee that you'll get your messages through them. The internet protocol says, oh, you can lose packets along the way. TCP is on top of that, saying that I can set up these sessions to sort of guarantee that I get my messages. There are other protocols, simple mail transfer protocol, how to send email across the internet, hypertext transfer protocol, and all these different protocols. There are thousands of them, and thankfully Java understands them and has a bunch of classes and hierarchies that allows you to use these protocols, and is a very powerful language. So that's a brief overview of the kinds of things we'll be talking about this semester in class. Remember that we're really dealing with computers. They're very simple. They basically fetch the instruction, execute the instruction, fetch the next instruction. They receive input from the outside world. They do this processing and they produce output. And they have a very simple concept of, I do one instruction, I do the next one, I do the next one. I have the control structures that allow me to do looping. I can do branching, so I can go make decisions. And then I have subroutines that allow me to build these blocks. I can then build up these modules that have data and these subroutines. We call those objects, that have data or state, and they have messages or behavior based upon calling these subroutines or functions, often called methods. And then we can build these complex things like the internet and build up programs. So I'm excited to be teaching this class. I hope I've given you a brief overview and not overwhelmed you with the kinds of things we're doing. It goes from simple to complicated very quickly, but we'll do it in a step-by-step process, and hopefully we'll have a good semester. Thank you.